So when we compare these venturometers, the advantage of these, first of all, it doesn't have differences compared to the weir, the potential energy differences compared to the weir. It enables to have a measurement in low pressure drops as well. It's suitable for unclean water if you have a high water cut. So it's suitable for unclean water as well. It can measure without having any problem. It's very good. It shows a very good performance in especially in wet gas measurements. We described these wet gas, dry gas, retrograde, volatile last week, right? These types. So it's good at wet gas measurements. Okay. But it has some challenges and points that device can have some problems. It does not applicable with the nonlinear flow characteristics. Just has to be a linear flow to get good results. Channel constriction resulting in damming of the heat water and risks of the deposit build up in the event of velocity decrease. Sudden velocity decreases can give some problems in this. Gives the loss of fluctuations. Actually, these fluctuations will be harmful for your data. So it has risks of plugging through larger floating items. Backflow is one of the biggest problem in here. If you have a backflow, then it make your measurement impossible. You cannot expect any correct results with this one. Backflow is one of the main problems. These we were facing when I was in Basra. We were facing with this one. What happens when the stock tanks are full? Okay, but you want to continue to your flow without knowing it. It's operational issue, of course. Without knowing it, you want to continue to your flow, but your tanks are full, so it's making a backflow. So because of that, directly you are seeing very big fluctuations in your data. So gives very high error percentage at that time. You cannot get any production results. Okay. So it's one of the main issues of this venturometer. And quality and reliability of the measurement, depending on the connected sensor, is another issue. The connected sensors, the quality of connected sensors is one of the main issues as well. If you have a bad quality one, so you can your error percentage increase. Some companies, some mid-range of companies are using, for example, the Venturi section in different company, and they are putting their own sensors, pressure sensors, so it creates another problem as well. These tools have installation costs. It's costly, like correlosimeter. Its initial costs are high actually. So this can be given to venturometers. Another one is the positive displacement meters. Okay. Positive displacement meters can be in different types, like different shapes as well, like overgear piston, rotary, rotating disc, etc. So this can give the conformity of using the correct shape according to your design. Okay, design of your production line. Another thing is excellent in dealing with the steady flow rate in a pipeline that has a diameter of 10 inches or less. Above 10 inches, it creates problem, increase the uncertainty on your data. But below 10 inches, you can give, if you have a steady flow, you can get good results. Applicable in low flow rates with high accuracy. So especially we were using this one for low flow rates. With low flow rates, your accuracy will be higher compared with the higher ones. Okay. So positive displacement, one of the negative effects on the measurements. Positive displacement flow meters doesn't have required industrial approvals for application in the field. It doesn't have too much applications currently worldwide, so it needs to be approved in the field site. It definitely needs to be approved in the field site, and standardized also. And this is needed as well. But in the future, it will be one of the good selected preferred meters, of course. So vortex meters. Actually, these vortex meters, a vortex flow meter measures flows of liquids, gases, and steam by sending the frequency at which vortices are alternatively shed from the bluff body. Okay. The frequency at which the vortices are alternately shed is directly proportional to the flow velocity. Flow measurement performed based on the vortex principle in here. Inside each vortex flow, a meter of the bluff body is located in the middle of the pipe. Okay, so this body is a kind of obstruction that disturbs the flow. And the vortices are present either the side of the bluff body and are carried away by the flowing fluid. The zones of high or low pressure appear downstream and thus create a phenomenon that's known as the Karman vortex street. So it's much more detailed technical part of this. This Karman vortex street, it used this one to have the measurement. Okay. These vortex meters are extremely versatile, can measure the liquid, gas, and steam. It gives relatively high accuracy compared with the others. Okay, it doesn't have moving parts, so it's simple design it has. This is a very good advantage. Also, multivariable meters provide mass flow measurement. The tools have API standards developed for the use of custody transfer. This is an important one because if when you use these standards, you guarantee that you will not have you decrease the risk of having any problem on your device. Okay, so this is a good one. The problems, the negative things about these meters, it can cause some pressure drop due to the presence of bluff body. Okay, there can be some sudden pressure drops. So these affect the results of rates. And of course, still, it's the custody transfer is limited. Okay, it has a standard for this, but it is limited. But in close future, this will be more widely to transfer as well in terms of transferring and in terms of usage. Okay. The orifice meters, these instruments are one of the well-known ones, actually. One of the well-known ones, and it's cheap ones because being cheap, the companies, especially mid-range of companies, are preferring this too much. So this is an instrument. That records the flow rate of gas, especially. We are using this for gas measurements through a pipeline. The flow rate is calculated from the pressure differential created by the fluid passing through an orifice of a particular size, of course, and other parameters such as static pressure, temperature, density of the fluid, and of course the size of the pipe. Okay. So the advantages of this, the orifice is small place and easy to install and remove. It offers a very little pressure drop, from which 60 to 65% is recovered. Okay, this is a good advantage. Because when it requires large pressure drops, your fluid cannot assess this one, your wellbore fluid, so you cannot have a good measurement in this case. The orifice meter can be easily maintained. This is a good one. Wide range of flows it can measure as well, but mainly are using it for. They have a simple construction, easily fitted between the flanges. Very simple design, so it's very easy to make the construction of that. and fit the instrument in between the flanges, as can be seen in the picture. Okay, here in for example, these are the flanges. Okay, these are the flanges, and you can put your orifice plate directly to here. And how it works, it's according to the difference of the volume that the flow is going through. It calculates by using the data in your orifice plate. Okay. Of course, they are the most suitable for most gases and liquids. I said they are very cheap compared with the others, and the price doesn't increase dramatically with size. According to the size, doesn't change when you compare with others. For example, Coriolis meter size, the price changes with the size a lot. Okay. So, what are the challenges and problems we are dealing with for orifice meters? It requires a homogeneous fluid. It's one of the issues. So, because of that, we are using it for gas, because when you go to, for example, when you are measuring the retrograde fluid or volatile fluid, whatever, so your error percentage increases directly. So, requires single phase liquid. It requires the flow of axial velocity vectors, some more technical. It causes a pressure drop in the liquid. Of course, there must be a pressure drop. You are trying to satisfy that pressure drop because the design shows it as well. Okay. The accuracy is affected by the density, pressure, and viscosity of the fluid, of course, like the others as well. This is surely. The range of measurement of viscosity limits of fluids. Viscosity can be a problem as well in here. For heavy oils, your error percentage will be increased as well. Okay. It requires straight conduits to ensure accuracy is maintained. Okay. The pipe must be totally special for the measurement of the flow of liquids. It has low range capacity. These can be given as the challenge of these orifice meters. So I tried to explain the single phase meters to you. Okay. So let's go through to separation based techniques. Okay. What are the separation based techniques? Sorry. First of all, the rate measurement accuracy and the resolution is quite important in well test analysis. For example, reservoir engineers often complain about the lack of reliable rates and rate inaccuracies as well, because how accurate you get your results of rates, you can use it. You will use it in the interpretation of your downhole. For example, especially in cleanup period, it's with the conventional techniques, it's impossible to get the cleanup period rates. Okay, this is crucial, earliest time rates, and they are very crucial to describe the parameters of your reservoir, your permeability, skin effect, your porosity, and the behavior of your reservoir in your well test analysis. So it's very crucial to gather the rate results correctly. Okay. So secondly, the separation is one of the simplest way to measure the flow rates of each phases separately. It also brings some sort of problems which can make things difficult. Okay. It simplifies the problem of determining the velocities as fractions. However, the quality of separation becomes critical and one of the most important factors which affects the error percentage and uncertainty on your measurements. Okay. So additionally, there is a need to use some indirect inputs. For example, rotation speed for the vortex meters, for example, rotation speed, pressure differential, as I mentioned. So these requires extra calculations, and these calculations gives you the results that you are getting is the result of these calculations because quantitative measurements. Okay, so in spite of the direct measurements, you are making the measurements with as a result of calculations. Okay, measurement plus calculations, so increasing the error percentage. Okay. So these extra calculations make the work more human dependent. Thus, the operator reliability and intention becomes crucial in separator-based techniques, separation-based techniques. Okay. So herein we can see the diagram, classical diagram. Your reservoir pressure and temperature, your well bore, you are reaching to your wellhead pressure and temperature, and you are passing through to your line. You are in your line conditions. Mostly we are putting, but if a company want to use multi-phase flow meters, your multi-phase flow meters will be mostly in this part. Okay. Of course, some other versions that you can use only in single phase. I am not accounting these ones for multi-phase flow metering. I am talking about. For multi-phase flow metering, your device has to be put in here in line conditions. It's very important. It will not be separate from the line. It has to be in your a part of your line. This is one of the crucial points. And then we continue to our way. We come to our separator. Your separator pressure and temperature you separated your liquid, gas, oil, water, and gas, of course. So you have, you calculate your certain rates of each phase in here when it goes out from your separator, and then you put it to your stock tank. Your oil comes to your stock tank, gas goes according to the situation. It can go to flare, it can store in somewhere. But for your oil, it is taken to your stock tank to wait to become that oil. Actually, after a while, it becomes that oil. Some part of the gas which included inside the oil as a solution has gone out as well, as I mentioned in the second week. And what happens? Your that oil, your stock tank oil, becomes available after 12 hours at least. Okay, and you separate your gas, another part of your gas in here too. So of course, all these steps will have different phase diagrams. Okay, you have different phase diagrams. Let's pass to this phase diagrams. For example, in your reservoir, you will see a phase diagram like this. What type of phase diagram is this? When we compared it to last week, I can say it's volatile, nearly volatile, but it can pass to retrograde as well. Okay, according to the shape, I can say that it's on the way of passing to retrograde, but on the volatile part, right? So in your reservoir, it comes through to your wellhead, your wellhead conditions change, and your phase diagram also change. Okay, it comes to your line conditions in your multiphase, your phase diagram will change again. In separator also will change, or also separation will occur. Your after separation, your gas phase diagram will be like this, because according almost dry gas you have, right? Almost you have dry gas. So in your oil also, the shape of your phase diagram will change as well. So when it comes to your stock tank, of course, your phase diagram of oil will be more white. It will be widely shaped. It will show, and gas will show nearly close to a line. It will show something. The balloon, we say, balloon shape will be close to a line. Okay, so we have to assume when we are making our calculations, all of these, according to the situation where we are measuring, okay? So fluid phase diagrams along the production, for example. As I mentioned, the big phase diagram shows actually the fluid characteristics in your wellbore, right? So this is your initial reservoir condition. Your bubble point pressure is here, your critical point here. Reservoir fluid phase envelope described in here. So what's going on when it comes to separator? So separator oil envelope will be like this, and gas envelope will be like this. Okay. Because why? Because the composition of your fluids changed. Composition changed. Because of the composition changed, your light components will be separated from the heavy components. Heavy components will form a diagram like this, and the light components will build a diagram like this. Okay, so according to your composition, your phase diagram changed directly. So when we compared according to this main phase envelope, which includes the composition in your reservoir, in your valve also, same composition nearly. So according to this phase envelope, we have to describe some certain points. What are these? Initial reservoir condition. Okay, first of all, your initial reservoir condition, we call it PI and TI, right? So your bubble point here, your multiphase flow meter conditions. I gave the example here. Your multiphase flow meter conditions, your separator conditions, and your stock tank conditions. Okay, we have to describe these 5 points by measurements, of course, by measurements. So the CGR, condensate gas ratio, and GOR, gas oil ratio, the ratio of these two also need to be described. This is the function of the separation process actually. The test should emulate that independently of metering conditions. So when you describe this ratio, it can give you the idea how much your composition changed. Okay. So for example, in here, your phase envelope is available. For example, 3000 psi, 190 degree Fahrenheit. Your condensate gas ratio measured as 64.6. It changed to 83 when it comes to 2000 psi with 160 Fahrenheit. And 1000 with 100 degree Fahrenheit, your condensate gas ratio comes to 97.7. Okay, so it directly changed. So each point is crucial to make your measurements. Okay, your measurements in your separator, in your stock tank, multiphase flow meter, as well as your wellhead. So in the surface part, it's crucial to describe each parameters of these, and you have to make your rate, pressure, temperature measurements, each steps, each parts and tools. Okay. Yes, here in condensate gas ratio is changing by time according to your place. According to your place, sorry, not time. According to the place, that's your fluid flowing. Okay. So the separator performance. Okay, let's talk a little bit about the separator performance. For example, in a very well designed and applied separator test, let's assume that we have everything is on the way. Very efficient test we have done, very well designed and applied the separator test very efficiently. Even in these conditions, the separator can show you plus minus 0.1 accuracy. Okay, but in these measurements, you have to ensure that each device is within its operating range. Each device is properly calibrated on time. All inputs are accurate, and you are interested in race at metering conditions. Okay, so I am assuming that everything is on the way. All devices and sub tools are working on the way. Okay, working correctly. But this is theoretically, of course. In the practical applications, this could not be satisfied. Okay, could not be satisfied. It's very hard to satisfy it. I did not see any case like this. So the separator uncertainties are essentially unknown and very dependent to its measuring conditions. Okay. So it's important to note that typical accuracy when we compare to all cases, of course, more and less, but the typical accuracy range is between 5% to 10%, we can say. It's far away from plus minus 0.1% accuracy. Okay. So in many cases, you need to have more accurate measurement results. And multiphase flow metering satisfying this one in most of the game and satisfies this one. Okay. So at this point, we said multiphase flow meters involved to the game. So let's see the market and what type of devices we have as multiphase flow meter using in the oil and gas industry. So these are the main multiphase flow meters available in the market currently. Of course, some new technology development versions of these available, but mainly these tools are dominantly used in the market. It's Halliburton tool. Expro and Roxar has multiphase flow meter. Schlumberger phase tester and phase watcher. Weatherford Red Eye it has. Roxar has Vector. Medenk, Solartron, and Hymo also has multiphase flow meters in the industry. In the future, when you see these names, so you have to be familiar with this one. That's why I'm giving this slide to you. Here, in what we can say in terms of the performance and effectivity, also there are some case studies available in the literature which compares some devices. As I know, one of them from Oman, and compared these devices. And the Schlumberger device, the phase tester and phase watcher, has far away in terms of the performance and the rate results. The validation tests has been performed. It is far away. It shows a good accuracy and better performance compared with the others. So in some part of my presentation, I will go through how it used and its working methodology, calculation overview. I will try to give these ones as well. Okay, so these multiphase flow metering, when we separated the phases as exploration, development, and production. For the exploration phase, three main multiphase flow meters are separated from the others. Okay, these are, as I mentioned, Schlumberger phase tester and its mobile multiphase flow meter as well. Halliburton device and Roxar also shows better performance in terms of exploration. Why we are saying in the exploration? Because in the exploration phase, you just finished. You have limited wells in your field, right? You have limited wells, 1, 2, 3 wells, whatever. So you are in exploration phase. You don't have any idea regarding the reservoir flow, your zones, the productivity of your zones. You are not sure about that. So your ranges are not known well. Okay. Because of that, devices has to be, as the accuracy of the measurement devices are very crucial in this point, right? So according to the case studies and literature reviews, these three devices shows a better accuracy compared with others in exploration phases. So when it comes to the development and production phases, of course, you have more idea regarding on your reservoir. You know what type of fluid you are producing, what are your productivity index, okay, what type of recovery you have from your reservoir, right? So because of that, you have more idea regarding on the characteristics of your field. So at this case, you can use, of course, Schlumberger device, Halliburton, Expro, Weatherford as well, Hymo and Medenk are useful when you are making in the future, if you face with this type of issues, when you are making your decisions. First of all, you have to describe which part of the product, which phase I am in my field. You have to describe this one, and then according to that, you have to select your tools. Okay. So another thing is when you pass to production part, what happens? You can of course use your mobile multiphase flow meters, but also there are some permanent multiphase flow meters as well. So what's happening? These are Schlumberger device is of course one of them, the phase watcher. Vector, Hymo, and Solartron has another permanent devices. Okay. So these are used in the field directly without taking it out. Okay, it becomes a part of your well, your field, your line, and stays in there. Okay, these companies also, as far as I know, they are also giving the training to the crew as well. The training to the crew. Some of them maybe maintenance I don't know, but giving the training to the crew to use the device correctly and making the maintenances. For example, for Schlumberger, as far as I know, they are coming in every 6 months. The Schlumberger crew making the to make the maintenance and to ensure that everything is on the well. On everything is going well actually. So these 4 devices can be used as permanent multiphase flow meters as well. Okay. So okay, we mentioned the single phase meters, so we gave the types of them. Now I would like to give the types of flow multiphase flow meters as well. Okay, so these are Venturi meters, cross correlation meters, single energy gamma measurement, the meters that make single energy gamma measurement, I will mention in details, electromagnetic measurement devices, microwave devices, ultrasonic devices, and the latest technology, the dual energy gamma devices, which compared more accurate compared with others. Okay. So let's start with the Venturi for multiphase metering. So these Venturi devices actually can make a robust mass rate measurements with moderate sensitivity to fractions compared with the others. Okay, moderate sensitivity we can say. It's quite straightforward measurement given a good density input. So your densities has to be very accurately measured, because density is one of the dominant factors which affects your rate results directly. Okay, so non-intrusive and well accepted. These are the strengths of these devices, we can say. But the weakness, it's designed for a single phase flow. When it passes to two phase, so your errors on your rates are increasing. You are starting to see more fluctuations. Okay, more fluctuations. It affected by discharge at high viscosities. Viscosity is still a problem here as well. Application to multiphase flow strongly dependent on a good slip law flow model. Okay. These are the characteristics of the Venturi device for multiphase metering. So another one is cross correlation. Cross correlation device. One of the examples is MFI cross correlation velocity meter can be seen here. The strengths can be given as direct measurement of phase velocities, not requiring slip correction. This is a good one, because the device is simple when compared with the others, as you can see from the picture as well. So wide velocity turn down it has, and the weaknesses, it assumes that the presence of markers in flow. Okay, it assumes that the flow is a stable flow. Okay, it doesn't have any fluctuations. It assumes this one. So it can be affected by the distribution of components. For example, you had some condensate banking in your wellbore, condensate banking, heavy components parted in your wellbore, and with the wellbore, that heavy components start to move through your multiphase meter. When this meter faces with that components, so directly it fluctuates. It could not separate that. These are a kind of condensate banking. Okay. So it's a bad problem, because it shows the same thing for foams as well. Foaming can be an issue when there is a foam in your wellbore. This also shows some fluctuations and increase error percentage. So single phase gamma, this uses the direct density measurements. It's relatively simple inputs with moderate margin for error. Okay, acceptable. It has a simple measurement independent of flow distribution, and it does not require gamma windows. It does not require gamma windows because it's just using the single energy gamma. I will explain these one, what I mean. it's a little bit, it uses a nuclear source, okay? It uses a nuclear source, and from this nuclear source, the gamma ray photons collide through to your line, okay, through to your line. As I mentioned, it becomes the part of your line, right? Your flow is coming directly, and this gamma ray photons passing in cross section as a line, and what happens? It collides with the molecules of your flow, and according to that, it gives you a result, okay? So, gamma windows is these gamma photons has a window, okay? This gamma photons has a window, and some points which shows some peaks, okay? So this just use one peak. Because of that, it doesn't require the whole gamma window. It just requires one peak. It just uses one peak. So the weaknesses, it only provides density leading and requires additional fraction measurements, typically water. So it's not good for water measurements in here, okay? So this is the earlier versions of the dual energy gamma systems. Because of that, it has these side effects, okay? So it has some sensitivity on composition that's oftenly ignored, okay? The composition changes. It shows some varieties, but oftenly this ignores. This is the, so what happens? It of course it increases your error percentage. Okay. So let's pass to another one, the electromagnetic measurements. I will turn back to this single energy gamma when we are doing gamma because the improved version of that. So electromagnetic means this used direct measurement of water, okay, water content. It's robust to hydrocarbon composition as permittivity is quite invariant to non-polar hydrocarbons, okay. This is the good one because, for example, the dual energy gamma, when you have a water, okay, you are producing just water, 90%, 95% water, or you cannot put it to any other parts. For example, you just want to measure your water, you cannot do it because it has been described according to oil, gas, and water. Okay, you have to describe all three. You have to give input to all three. Okay. So this is a strength for electromagnetic measurement. Okay, but the weaknesses, it depends on structure of flow. For example, bubble size, elongation, continuity. These affects the results. It depends on water salinity. Water salinity, when the water salinity increase, or you cannot give water salinity input, okay, or different input you give, your rate results change a lot. So this is another problem. It has iterative solving, not direct physics. So it works, the calculation works with the iterations, okay. The capacitance shortcut in water continuous flow and inductance in oil continuous flow. These are the weaknesses of the tool. So another one is the microwave measurements. I will describe the microwave measurements as well. So in these tools, the transmission measurements can capture resonant frequency and be a good measurement of permittivity. This is a good one. Provides both water fraction and properties. That's good one as well. Measurement resolution currently actually we said low. Okay, measurement resolution low, not now. It's not. Some companies are producing these tools, and they are saying that the accuracy, the resolutions are in these values, but it's a little bit tricky, and it's a little bit tricky, and it gives a kind of problem, of course, to you. Okay, so herein. I will go through the weakness of this. Okay. There is a question, I think, what is permittivity, they said, right? I'm checking from here. Okay. So permittivity, what we can say, permittivity is a constant value that we use it in the calculations, and it says it gives the amount of the dielectric constant. Okay, dielectric constant. So it's a technical value. It's a technical value. So we have to go through to calculations of these microwave measurements, but it is, we can say that it's a kind of constant change from one measurement to another, actually. Okay, according to the characteristics of your fluid, it changes from one measurement to another. Okay, so that's what I can say about the permittivity. Okay, so what we said, it's complex model to invert, simplified through correlations. You are welcome. And the measurement can saturate sensors. Okay, so when we compared all these measurement tools, actually, we see error percentage, which some of them are higher than even separator results. Okay, some of them is lower, of course. Some of them is higher compared with separator results, especially if you are using a new technology separator. You can get close results to new versions of the multiphase meters as well. So from this point, I will continue with the one of the latest technology and one of the best methods that applied in the industry. We call it dual energy gamma system. Okay, dual energy gamma system. This dual energy gamma system is collocated fractions measurements. Okay, it's the strengths, we can say, it's collocated fractions measurements. It gives you the measurements of your fractures, first of all. Okay, it unaffected by emulsions or foam. As I mentioned, there was a condensate banking and foam flow. It can fluctuate a lot, right, in the previous devices. So this is unaffected by emulsions and foam. The hardware is simple hardware it's using. It's a single physical phenomena for both gas liquid and water liquid ratios. Okay, when you are calculating these, it uses a just single physical phenomena I will mention. It has certain rates of individual phases in lower error percentage and less inaccuracy compared with the other techniques. Okay, so the weaknesses we can mention here. It uses reference measurements. Okay, the attenuations, the mass attenuations that you get as a result of these reference measurements are crucial. Okay, you have to make correct measurements, and the device is so sensitive to these measurements. Okay, so another thing is sensitive to composition change as well. Sudden composition change, we can say. It affected by high frequency noise. Multi-energy sources create downscatter and measurement challenge. I will mention these as well. When we give the calculations, we will be more clear. So it has limited accuracy on small fractions compared with the other. It has limited accuracy on small fractions compared with the other tools. Okay, I can say compared with the other tools. So I will go through one of the best tools in the market, the VX of Schlumberger. Okay. And the working mechanism of these as a dual energy gamma source. Okay, I will continue with this tool from now on. Sorry. Yes, so this tool is efficient and reliable for the measurement in wide range of fluids. Okay. It's a new technology, of course. Actually, Schlumberger declared another tool. They are using that one, which gives the whole spectrum of the gamma ray spectrum. It calls spectra. This is the previous version of that I will explain, but similarly, the methodology is same. There is no difference. Just one difference I will explain. So this multiphase flow meter is used to measure three-phase flow rates, oil, gas, and water, without any separation needed. You don't need any separation. Your oil, water, and gas flowing through to your pipe directly as a line. Okay, it's a part of your line, and your three different phase is continue to flow. And by using this method, these two, you are measuring the rates of each phase differently. Okay, you are saying in that you are saying your oil rate is this, gas rate is this, and water rate is this, that's flowing in your line directly. Okay, so we mentioned the Venturi and we mentioned the dual energy gamma system. Okay, so this technology is the combination of these two. Okay, Venturi is used for the calculation of total mass rate, and dual energy gamma system is used for the calculations of phase fractions. Okay, and a fluid model combines these two and gives you the rates of individual phases. Okay, it works like this, basically. It has three different tools. One of them is mobile onshore, mostly in exploration phases it's used, as I mentioned, and also another usage type is if you have a big field, with 1,500 wells, for example. Okay, you are in production phase, of course. The field is well known. You are in production phase, but what I mentioned in the first week and in the last part of the first week and in second week as well, we were issuing with the water production, right? We are dealing with the water conning issue if you have an aquifer in your reservoir, right? So to prevent this water conning, you have to make continuous measurements, we mentioned, right? How you will make these continuous measurements? Well by well, you have to be sure about your flowing rates, your pressure and temperature data, right? So by using separator, if you use it by using separator, you need 1,500 separators separately built in your each your wells, right? Each part of your wells. Okay, so this is not useful. So what you will do? Okay, what you will do? Normally, what's happening? Your, for example, 50 or 60 of these 1,500 wells is connected to with a line. Is connected to a degassing station, for example, right? And your separators in there. But it's not useful. It is not meaningful to get the result of 60 wells. Okay, so what I will do? Then I am using this device, the mobile device, multiphase flow meter. I am going through to each well separately day by day. I am measuring one well. I am measuring the well for 1 day long. I'm passing to another well in the second day, passing to another third well in the third day. Okay. So what's happening after one month or 1.5 months in one location? I have a good mapping of this location. And the continuous monitoring, make it a continuous monitoring available. I am seeing which part of this field has water conning. So I am lowering my rates in that part and lowering the production as well, and increasing the production in the parts that has lower water fraction, right? So because of that, this is very useful, especially in production wells, to make a continuous reservoir monitoring. The second one is the permanent offshore one. The permanent offshore one. This mainly used if you are in exploration and you are not in exploration phase. Sorry, you are in production phase, development and production phase. You are okay. So, for example, you have an early production facility. You are passing to production phase. You are end of your development phase. You have early production facility. You can install this device. It's a permanent device. Okay, it's installed directly. and becomes the part of that structure, that production facility. It can be used this type of places actually. Another one, this is also permanent. This is subsea version of that. It used in offshore wells. It designed according to the offshore well structure and design. Okay, so it used in offshore wells. This is the third version. Of course, this also used in the production development phase. Okay, so let's a little bit come into details of the devices, how it works. Okay, so this is the general view of the device. Okay, so what are these sub tools of this device? First of all, there is a gamma ray smart detector, as can be seen in here. Okay, this enables to measure the gamma ray counts passing through the fluids at the venturi throat. Okay, at the venturi throat, and it detects the counts sent by the source and reflected from the molecules of each phase. Okay. As I mentioned, there is a venturi section. This is a venturi spool. This used to cause a kind of line size restriction between the vertical section of the inlet tool and the throat. Okay, line size restriction is important to calculate the pressure differential as well. Okay, so it's a kind of conventional venturi. Think about conventional venturi in the vertical direction we are using it. So it has three sensors: line pressure transmitter, differential pressure transmitter, and line temperature transmitter. Line temperature transmitter is put in a different place compared to these two close to the venturi section, but the laboratory measurements, Schlumberger laboratory measurements, show that the best representative temperature value can be get in this section. Okay, when it collides with the wall of the pipe, closed wall, when the fluid collides with this part. Okay, and it mixes. The best mixture can be get here. So the line temperature transmitter they put here. Okay. And another thing, we have a radioactive source. We call this device use barium 133 as the source, and it gives gamma photons. Okay, gives gamma photons through to the center of your venturi. Okay, the center it has the lowest radius. It sends the gamma photons through to this line. Okay, and what happens? Your flow is coming in upper direction. Okay, from the lower part through to upper direction. Your three-phase flow, oil, water, and gas flow is coming through to this, and this collides with the gamma photons. Okay, and gamma photons lose its energy when it collides with oil molecule. It loses its energy. When it collides with gas molecule, it loses its energy, some part of its energy. But the energy amounts that it's losing is different in different phases. For example, when it collides with oil molecule, it loses different value of energy. Water different, and gas different value of energy. So because of that, what happens? And I know the certain energy amount of the gamma photon. Okay, I have the value of that. It's a certain value. So after the collision, what happens? It reflects, and there is a plate in here. That plate gets this reflection, the gamma photon. When it reflects from the molecule, it directly goes through to the plate. Okay, this makes it in 45,000 times in a second. Think about that, 45,000 in a second. Okay, so it gives you the repeatability is very high. Because of the repeatability amount, it gives you a very good average result. Okay. So these mass attenuation, we call it mass attenuation. Okay, it collide, it lose some part of energy and reflect to the plate, and you make the measurement. You are getting the measurement of this mass attenuation. How much of its mass lose, and what is the molecule that it collide? It says that it collide with oil molecule. It says that this molecule was a water molecule, and it's making it 45,000 times in a second. Okay. So, as I mentioned, it comes to the gamma ray smart detector, and there is a fraction meter in here. So it changed these reflections through to electrical signals and sent it to computer. Okay. And from the computer, you directly read which phase it is. Okay. And what are the rates you are reading the mass attenuations and putting it to the calculations, and at the end you are getting the rates. How we will mention about it. Okay, of course it's very crucial in here to use to make the isolation. So the best method to make this isolation in this part, in the center of the venturi section, using ceramic material. For a nuclear source, you have to use a ceramic material. So ceramic monolithic windows, it has been used in this device as well. Okay. Yeah, as I mentioned, gamma ray smart detector and data acquisition flow computer, diffractometer passes the electrical signals to the data acquisition flow computer, and you make your data read in there. This is the actual device, as you can see. So it's part of your line. How it becomes the part of your line? This is the inlet part. Okay, your flow comes from your wellhead, from your well bore wellhead, and comes through to here. Actually, the length from your wellhead in here may be 5, maximum 10 meters. Actually, okay. So it becomes your line. It comes the inlet comes through to this way and comes in the upward direction. The measurements becomes in here, and then it continues through to its way as an outlet fluid, and we sent it to separators, right? Okay. So now we mentioned about how it's making the mass attenuation measurements. Okay, but how we will use this? These raw measurements used for the calculation of flow rates. Okay, flow rate calculations. Actually, let's start with this one. In total, only 4 sensors, as I mentioned previously, are used for the purpose of flow rate calculations using this technology. Okay. Sorry, these are the differential pressure across the venturi is used to determine the total flow rate of the mixture. Okay. The gamma ray detector provides nuclear attenuations of the flow stream in 2 distinct gamma ray. Okay, so it's used to determine the phase fractions. Okay, to the phase fractions, and then the pressure and temperature measurements are used to determine the relevant fluid properties, essentially to convert flow rates from metering line conditions to standard conditions. Okay. So these used to determine the relevant fluid properties. So let's visualize this. How we will do? You have a venturi and you have a delta P in this venturi. Okay, you have a venturi and delta P. So you are putting the results that you get from here in your venturi section to a fluid dynamics model, and you get the total mass rate. Okay. On the other hand, you have a source and detector in here, right? We mentioned. So your source and your detector making another measurements, nuclear measurements, right? Gamma ray measurements. So you are putting this through to another nuclear model, and it gives you the phase holdups, okay? The persons of individual phases. It says 60% oil is producing, 20% water, 20% gas, okay? So you get your phase hold-ups with this one. And in the end, it combines these two. It's in my packet. This is in my packet. When I get these two, I will combine these, the total mass rate and the phase hold-ups in fluid properties model. Okay. And what I get, I will get the single phase rates, the rates of individual phases, right? Oil, water, and gas, I would say that. This is the visualized part of this. So let's go through to fluid dynamics model and nuclear model and fluid properties model now, okay? So fluid dynamics model, it uses, of course, everybody knows this, Venturi section, if it has a Venturi, so you have to use for the energy conservation, the Bernoulli equation, right? So it uses the Bernoulli equation for the calculations, also mass conservation, okay? And another ratio that I need to make my calculation is throat inlet diameter ratio, okay? I will use these three equations and I will get the total mass rate. Okay, this is the total mass rate formula that I get. Okay, but this mass rate, total mass rate calculation, of course, has some errors in it. These errors sourced because it didn't account the energy losses due to turbulence, the slippage effects between liquid and gas phases, and the expansion of liquids at the Venturi throat. Okay, so Schlumberger engineers handled this problem as well and developed a very good formula, which also accounts these steps, accounts these parameters as well, and they yield this total mass formula, and the calculation of this tool directly uses this formula, friends. Okay. So, what about the nuclear model? So, nuclear model, actually, nuclear topic is a topic that most of the petroleum engineers are not familiar with, right? But it's in terms of general knowledge, it's good to know this one, and I will try to explain. Okay, so we said that we have a source and we have a smart detector, and we are sending 45,000 gamma photons in seconds, okay, through to line, as we can see in here, right? It's passing 45,000 gamma photons in a second, right? So when passing through matter, gamma photons lose their energy due to collisions with the atomic particles. I already mentioned this. It reflected, the gamma photons reflected, reached to gamma ray smart detector and diffractometer. This also mentioned. The recorded gamma ray differences, the mass attenuations we call, describes the fluid type because it says that I collided with oil particle. I collided with water particle, water molecule, oil molecule, gas molecule, okay? Gives the phase hold-ups of each liquid in an operating triangle. You have to make, what I mentioned, you have to make, in first case, you have to make your empty pipe and fluid reference measurements. You will fulfill your Venturi with oil related to that well, with gas related to that well, gas sample, you will take oil sample, you will take gas sample, you will put to your Venturi and you will make your measurements. And air, empty pipe air measurements, okay? So according to these reference measurements, it will create, what happens? It will create a triangle, okay? These are the measurement results of mass attenuations, okay? If you produce 100% water, you will be, for example, in this point. 100% oil, you will be in this point. 100% gas, you will be in this point. So your measurement for this well, so in each well you have to measure differently. You have to, it's a procedure. You have to do the empty pipe and the fluid reference measurements in each well separately. So why? Because it directly identifies the characteristics of that well. So when I use my reference measurements and when I make my real measurements belong to that well, the result that I will get has to be between this inside this triangle. Okay. If I am going outside of this triangle, this is also cross check. If I am going out of this triangle, so what happens? There is something that I'm making mistake. Okay. It shows that I am making mistake. So the formula, the general formula it's using, as can be seen here, it's Nx, the number of counts measured, NO, the number of counts in vacuum. Okay. The distance, mass attenuation value, and the density. And the computer directly calculates this one by getting all these results. You also have your density result as well, mass attenuation result you have. The distance already know according to your venturi size. Okay, so you know the number of counts measured, and in vacuum also you got your mass attenuation results. So you have all the parameters, and the computer directly calculates it. So let's go a little bit let's talk a little bit about the physics of this. Okay, it uses actually three different when we said that it's colliding, when it's making this collision, there are three physical phenomena occur. Okay, well, one of them is photoelectric absorption, the second one is Compton scattering, and very rarely it's pair production. Okay, pair production is the electrons, one part of electrons get the positive load, the other parts get the negative load, and it shows pair production. This is rarely happens. Mostly in this barium 133 shows photoelectric absorption and Compton scattering. Okay. So what about photoelectric absorption? Photoelectric absorption is formed by the interaction of the incident photon with an electron from the inner orbital of the absorber atom. Okay, so in your it is a electron in the inner orbital. When it collides, the photon ejects the electron from its orbital and turns it into a photoelectron. Okay, after collision. At this point, the incoming photon disappears, and the kinetic energy of the photoelectron is equal to the difference between the incident photon energy and the electron's binding energy. Okay, so most photoelectric interactions occurs in the first orbital because the density of the electron cloud is greatest in the region and interaction is more likely. Okay, so you are in the first orbital, you are colliding, it's separated, the electron, and then after that separation, your gamma photon reaches your plate and the diffractal emitter directly get the amount of mass attenuation. Okay, so this is the first way. This is the most common way actually. Okay, in terms of percentage when you compare, this is the most common way. In the second one, the Compton scattering. Compton scattering. It occurs when a photon interacts with an electron in the outer orbit. In this interaction, the incoming photon collides with an electron from the outer orbital, giving its kinetic energy and causing it to eject. Okay. The direction of the incident photon changes and creates scattering in a new direction, different from the direction of the impact. And the energy of the scattering photon is found by subtracting the energy of the incident photon from the sum of the kinetic energy gained by the recoil electron and binding energy from the electron. Of course, to sum up, there are two ways of collisions. One of them photoelectric absorption. The other one is Compton scattering. Okay, one of them because one of them gets the electron from the inner orbital. The other gets the electron from the outer orbit. And these devices calculate these two mainly. Okay, pair production not too much. Pair production also calculate, but pair production mass attenuations when we see it's less than 0.1%. Okay, when we compare with the others. Okay, so let's move to the inputs determination. So what we said, I had my mass rate results. I had my fractions. So I got from my nuclear model, right? So I combine these two in a fluid properties model to get the real rates of individual phases. So I will use fluid properties model, but this is crucial to select the best model that fits with the characteristics of my well production, okay, my fluid of my well. So, for example, if you are dealing with the black oil, with a black oil production, black oil well, okay, so it's beneficial in terms of the costs as well. It's beneficial to use your black oil model, okay, standing correlation, the others, okay, you can use your black oil model direct, okay, so it will give you good results for black oil, no problem. But if you pass through to volatile, retrograde, wet gas, even dry gas, okay, so what you need to do is you have to use the results of your PVT lab measurements, okay. You will take the sample of your fluids. You will take sample of your fluids. You will make your experiments. Maybe if you have correct devices, you can do it in well site, or you will send it to a certain laboratory, and you will make your get your results of experiments, PVT experiments. You will put these experiment results through as an input value to your processor, which uses the fluid properties model and combines it with total rate and the fraction results. Okay, so this is one of the best methods using direct measurements. And another thing, if we have, for example, volatile oil or retrograde gas, sorry, you are producing. Another thing, you can use the equation of state modeling. So modeling can be a part of this as well. In Schlumberger, they have these models which resulted in having VX Fluids ID. They call VX Fluids ID. It gives the idea that it calculates and gives the idea regarding on 11 different parameters which required for these calculations. These are the densities of each phases: water, oil, gas; viscosities of oil and water; formation volume factor of oil and water and gas as well; and the shrinkage factors, RST, RWST for water, and RGMP for gas. Okay, so 11 factors is calculated by using this EOS, equation of state modeling, and this also performed by the PVT laboratories as well. Okay, so this is the example of VX that I can say. And now, of course, the usage of this method depends on the accuracy requirements, flow conditions, and fluid complexity. For example, if you have retrograde gas reservoir, you are producing retrograde gas, but you want to use black oil model. Some companies can say this as well. Okay, okay, use black oil model, no problem. Okay, you will have more error percentage and inaccuracy, but the guy, for example, in production phase, the field is in production phase, and he already knows the characteristics of the field, okay? So he can say that the error percentage is this. He can describe the error percentage directly, okay? Because the characteristic of the field is this. I am seeing the GR values, how much production I have, the rates, the pressures, everything I already know. I have 1,000 wells. So because of that, just making this experiment, this measurement, to have a rough idea regarding on that part of the field, okay? So he can use the black oil model even in retrograde, but it directly depends on what you need actually. Okay, if you are exploration phase, you have to get the best result, the most accurate result, because you want to get an idea about that field, right? So because of that, your requirements are very crucial to describe which models you will use. Okay. All right. So. Yeah, I mentioned in here already. For example, for black oil model, you are using standing method for oil volume calculation, right? It's valid between 25 to 40 API. And for equation of states, it's for Schlumberger example, of course, VX example. the VX fluid IDs for the 13 different parameters that describes the PBT of the fluid, and physical measurements. So in this physical measurements, there's another thing. I think this is only available in Schlumberger. This is only available in Schlumberger, and I think this is one of the best products. This called phase sampler. Okay, this called phase sampler. I will mention about this in next slides. But before that, I would like to mention about the operating envelope of this. Okay, I would like to mention about the operating envelope. For example, in this VX example, the pressure difference has to be between 50 millibar to 5,000 millibar. Okay, it has to be like this. If you are below 50 millibar, so fluctuations can start. So it changes their percentage, and if you are above 5,000 millibar, so you can have the same problems as well. Okay, so this is important. The second one is dPV divided by line pressure plus dPV volume. Okay, this ratio is important because this describes the sonic index condition. Okay, sonic index condition. If it is above 25%, then the Bernoulli equation cannot be used. Okay, it's not valid because the match number, which is the ratio of speed divided by speed of sound. Okay, this is the ratio. Mesh number exceeds one, and your Bernoulli equation is not valid after that time. So because of that, it has to be below 25%. So in this multiphase meter device, it has two different modes. One of them is oil mode, and the second is gas mode. If your GVF is between 0.2 to 96%, you can directly use your oil mode, no problem. And between 98 to 100, directly you have to use gas mode. But if you are using your gas mode between 90 to 100%, it's also valid, no problem. Above 90, you can use gas mode. There's no problem. It changes the calculations, different calculations they are using. Okay. So your line condition viscosity, another thing, your line condition viscosity has to be below 2,000 centipoise. Okay. So if you start to produce asphaltene and heavy components more, so of course it will create some error percentage in your rate results. Okay. So this has to be lower than 2,000 centipoise. This is fluid dynamics model limitation. So another thing, your line condition, line pressure. The pressure in your measurement, in the point of your measurement, it's a part of your line, right? So your line pressure has to be above 5 bar. If your GVF, gas volume fraction, above 80%, okay, it has to be more than 25 bar for all gas modes. Okay, if you are using gas modes, it has to be lower than 25 bar. So these type of limitations, mostly the operator, if for example you are a supervisor in an operator company, or you are responsible for the selection of these tools and applying one of them, you selected VX for example. So you have to know these limitations and when you are checking your result files. But in all cases, of course, the crew of Schlumberger are taking care of these. You have to know, but you have to know for cross-check, but they are definitely checking all the steps. Okay. So another point of the multiphase flow metering, another advantage of multiphase flow metering, it corrects your well test interpretation as well. It helps to correct your well test interpretation. How it's making this? Okay, here you can see some results which has been plotted by Ekrin. Okay, here in the first one, the derivative of the second build-up. This is the derivative of second build-up. has higher permeability compared with the first one, right? Because the reason, just adding the rate results of the earliest times, which comes matched with the cleanup period. Okay, what happens in your cleanup period? What happens? You just finished your drilling, okay, and you want to clean your well. Well, or you have to clean your well. You will start production. You will make your perforations, but before your perforations, even you have to clean your well, right? So you are making when you are making the cleaning, these are the earliest time of the life of your well, right? The earliest times. So the information that you gathered in here, rate information, is very crucial. But none of the tools like separators and other ones, none of them can do this. Not succeed to do this. You cannot measure cleanup period because you have some solid particles, okay, rock particles, whatever you have. You are cleaning. You cannot put this to your separator because your separator has problem. You will need maintenance. So because of that, this is the best way to use this one, a tool which is a part of your line directly. Okay, your line is already flowing, and you are making your measurements part of your line. Sorry. Any question? Okay, I'm continuing. So as a part of your line. Okay. So you can see the reflection in your permeability. When you have here, you can see the result of the earliest phase, cleanup phase. Your pressure value is here. Your rate value is here. You can see how fluctuating it is, but measured. Normally, what we'll do, you will use 0 in here. When you use 0 in here, you will get the result like this. But when you use the real rates, which belongs to that part of the production, so you will get your real permeability values. Okay. So it also affects your semi-log as well, right? So your P star as well. So it's very crucial to describe the cleanup period rates, and it's only available by using the multiphase flow meter. So multiphase flow meter usage is very crucial in early times of your well. Okay. All right. So impact on reservoir properties, as I mentioned, errors in rate translate directly into errors in permeability. Absence of rates makes any interpretation impossible or with high error percentage. The full rate history allows additional features to be analyzed, right? Rate dependent skin or boundaries have not seen from a single buildup. Okay. So when you made another measurements, even in your second, third build-up period you made, even in that parts, this correction in your cleanup period will totally affect. For example, you made your third build-up, you could not see the boundaries, but you don't have rates in your cleanup period. When you have cleanup period rates, you can describe that boundary. Okay, so it's very crucial. Okay. Another thing is metrological performance. We can see, for example, the red one is the model that I had done with the measurement of rates, and the yellow line is the production. See how it is matching. It's too much matching, right? It's already the same. Some little fluctuations, but it's already the same because I put the correct rates on the correct places in all steps. Okay, in all steps. So this enhanced metrological performance is very crucial to enable a high resolution, excellent repeatability, high scanning rate, and long-term monitoring is enabled as well. Okay, with this one. So it's crucial to combine your multi-phase measurements when you are making well test interpretation. This data is crucial. Okay. So I mentioned that I will mention about the phase sampler technology. This is the only tool applied in the market, actually. This enables to take samples in line conditions. Okay, enables samples to take samples in line conditions. You will not take it through to the atmosphere. You are not taking it from your separator. You are not taking it from your wellhead. Directly, you are taking it from your multiphase meter as a part of your line. Okay. So how it works? This is the tool. Okay, as you can see, it has three different probes. Three different probes. This is the upper part of the VX2. You put your sampler directly through to this part, okay? With these three probes come directly in the middle of your line, okay? So the first tool is in the upper part, in the center part, and lower part, the third one, okay? So your flow comes through to this. When your flow comes, the experiments show that most of the liquid phase comes from these two. Okay, these two parts, lower and upper parts. The fluid, the liquid, comes through to this part. Okay, sorry, but gas comes in the middle part. Okay, when it is coming through to this part, making a shape like this, the experiments show that gas is coming in the middle part and the liquid is in down and lower, upper and down part. Okay, so these probes is adjusted according to take liquid part from up and down and gas part in the middle. So it's taking just gas phase, the middle one, the other then it selects the gas. For example, in the middle part, it selects the gas phase. It selects the liquid phase, okay, directly. Even there are some liquids in this middle parts, it's not getting that, it's directly getting gas phase. Okay. So, as I said, operates at line pressure and temperatures, has flash apparatus that measures fluid properties at well site. There's another tool. When you get the measure, when you get your sample in the well site, there's another tool. You are directly transferring this sample and you're making your measurements. A kind of well site PVT tool, we can say, which includes even micro gas chromatography as well. Okay. So it requires no additional external power. It's directly compatible with these multiphase meter VX and can be used without any external power needed. Okay, so the benefits of taking the samples in line conditions. Okay, so I mentioned this when I was describing the phase diagrams in the second week, right? The best representative samples has to be taken, if you're in single phase, has to be taken from your reservoir arsenic, okay? Because when you come to the surface, it's separated. It can separate into two phase, especially in retrograde gas, for example. It will pass two-phase flow, so it will not be representative compared with the reservoir samples. So when you are getting in the line conditions, as for example, you have a volatile oil, okay, you are getting it from your line conditions in the surface, so it will be more close to your reservoir conditions compared with the one that you take from your wellhead, because when you are taking it from your wellhead, of course you are opening it to atmosphere as well, okay, or when you are taking it from your separator or stock tank. I'm not talking about stock tank, of course. When you are taking it to separator, when you compare these two, line condition sampling has more advantage because it's more close to your reservoir conditions, to your, in terms of liquid, in terms of fluid composition. Okay. So you can, it's enabled to get through single phase samples thermodynamic equilibrium always achieved. Okay, so what happens, for example, when you are taking it from your separator after separation, you have to recombine this. You have to recombine this. In here, you already got your sample and you are putting directly to your PVT well site tool, and directly it gives you, without any recombination, it gives you the result directly. Okay, so several cases where phase sampler samples were higher quality than separator pairs, of course. I said direct taking from line and using another probe. So the quality of your samples and representativeness actually compared with the separator is much more high. It's highly repeatable. How many samples you want, you can get. Okay, take out one, put another one. Okay. So in total, the advantage of multiphase flow meters, we can say, in terms of operation efficiency and safety, is compact, lightweight, and small footprints. Most of them has this one compared with the conventional meters. It has reduced crew, surface well testing crew reduced when you compare with the conventional ones again. Short operation duration, saving rig time and reducing flaring. Of course, when I said you are measuring 1 day long, actually it will not be, you can make 2-3 wells in 1 day long. If you are working 24 hours, three wells, you can do 3 wells without any problem. Okay. Saving rig time and reducing flaring, we said. We reduce flaring because you are not separating gas. You are already measuring from your line conditions. You are not separating gas, so reduce flaring. And saving rig time, of course. It's online continuous production monitoring enables, as I mentioned, in terms of your field monitoring, water conning issue. Okay. So no moving parts. So no moving part results in low failure probability, of course. And in terms of data quality and meteorological performance, I will talk. The data quality and meteorological performance, when compared with the conventional testing, it has improved accuracy. For example, here the results can be seen here. Okay, for example, the blue one you see. The multiphase flow meter liquid rates. Okay, yellow one can be seen here or not, I don't know, it's a little bit hard. The brown one is the gas results of VX. Okay, and purple one is the liquid of separator, and the yellow one is the gas separator. Okay, the yellow one cannot be seen clearly, I think, but let's make a kind of analyze on this. For example, you see the fluctuations of the liquid separator, right? It's lots of fluctuations, but in fact, in real, the results like the brown one, right? You see how it is. So it has, sorry, the results are blue one. So you can get easily the average rates, okay, in each phase, in each part, in each timing, you can get the average rates easily. But here you cannot get, it's very hard because your error percentage is higher compared with the blue one, right? So another thing, herein, maybe you can see, maybe you cannot, I don't know. Okay, let's compare this one. For example, the rates in this part, in liquid rates, shows a decrease, right, in the blue one, in fact. But with the separator, it's impossible to gather this one. Here, it shows the end parts, you can get the results. So it will, when you put these rates to your lattice interpretation, it will directly affect your results as well, of course. And another thing, there is a condensate banking occurs in here. The losing of heavy ends can be seen, but here there is no value of the separator. It's losing heavy ends because of the rate. The rate in gas phase is increasing. Okay, but your blue one, the liquid one, is not increasing, but gas is increasing. So it says that in terms of percentage, some part of the heavy particles are not showing up. Because why? Because it had some condensate banking in some parts of your valve. Okay, it's accumulating in that. So it indicates that one as well. Okay, so high repeatability. It has completely commercial ones. Independent of flow regimes, you can, each type of flow regime, as I said, from heavy oil to dry gas, you can measure this one, there is no problem. Exceptional dynamic response can be seen from the figure. Flow rate measurements during all cleanup. Okay, in the cleanup period, we already mentioned this one. You have cleanup rates and it directly affects your results. Okay. Early water detection compared with the separator or early water detection. So that's why they are using that for water conic issues. Not affected by slugs, foam, or emulsions. This is for the measurement of surface water testing. It's very challenging issue, actually, foaming and emulsions. So it's not affected by any of these because it's measuring in microscale, not a total measurement of flow. It's measuring in microscale. So because of that, it's directly, for example, a foam coming, a slug coming, for example. It just says that this molecule belongs to gas, this molecule belongs to oil, this molecule belongs to water. So because of that, it's totally independent from emulsions and foams, okay, and slugs also, of course. So unique hardware for heavy oils, black oil, volatiles, gas condensate, wet gas, and dry gas in lab testing. This is actually this last one is not valid for all multiphase meters, but for VX, of course, it's valid. Not all of them in this range operationally suitable, but for VX it is. So the things that I will mention is like this regarding on multiphase flow metering. If you have any questions, I will be happy to answer all your questions. Let me check. Okay. Any questions you have, Ras?
Sorry, I have a question.
Please.
So maybe that's not so related to this concept, but I have a question about PVT analysis. What's the difference of PVT analysis and phase envelope?
Can you please repeat the last part?
Difference between PVT analysis and phase envelope.
Okay, you are asking about what are the what is the effect of PVT analysis on the phase envelope when we are making multiphase flow metering measurements?
Yes.
Okay, so what happens? Let's describe the PVT measurements in this case. So you take your fluid sample in the surface or in your reservoir. Okay, you take this sample to your laboratory to make certain experiments which describe the characteristics, the composition, the characteristics of that composition actually. Okay, so first of all, you can make the composition analysis. How many percent C7 up to C7 and C7 plus, mainly. I'm talking basically, okay, or C36 plus. Okay, so you got your composition, mapping of your composition. Okay, how many percent methane, ethane, how many percent all of these you have. Okay, according to this composition, the second thing that you will do is to describe the pressure, temperature, and volume behavior of that composition. Okay, this composition it changes from one well to another, even in you are producing from one field. Okay, your neighbor well can be different. Your well can produce different composition. Okay, this is possible. So each well, or maybe you are producing from multi sections, right? you have different phase zones. You are producing from 3 different zones in one section. So the amounts are coming, it's a commingled flow you are producing. So the amounts and the compositions can be different. So for each well, you have to do these measurements, these sampling measurements. So you define your compositions. You are, and then taking the sample through to PVT experiments. It describes according to a certain volume and the volumetric change, how the pressure and temperature responds. Okay, so you get your pressure, temperature, and volume, behavior of that fluid. Okay, normally this is the plot of this is the 3D plot. Okay, so it has 3 Cartesian x, y, z, and describes your PVT behavior. We are using in this one just the pressure and temperature behavior. Okay, just the pressure and temperature behavior. Pressure and temperature behavior phase envelopes we are using. Okay. So what it says physically, it means that in a certain volume of fluid, the pressure and temperature behavior is like that. Okay, in a certain volume of fluid, the pressure and temperature behavior is like that. So when you get this phase envelope of that fluid, what you will do, you will describe in the reservoir, I am in which part of this phase envelope. Okay, I will check my pressure and temperature of my reservoir, and I know my composition's phase behavior. I will see that, okay, I am in single phase part. Okay, I am in single phase part. When it comes through to your wellbore, what it happens? When it comes through to your wellbore, your pressure will decrease, and some part of your pressure, your temperature will decrease as well. So what it will be, if you are producing from a retrograde reservoir, for example, when it comes to your wellhead, somewhere between your reservoir and wellhead, it will pass to two-phase flow. Okay, when it reaches to your wellhead, it will be in two-phase. So it will be inside your phase diagram. When we talk that phase diagram, so some liquids and gas, it includes, so you will be inside your phase diagram. So you will describe that point as well. In your wellhead, you will be in this point. So let me explain. Okay, let me explain this by using, I had a figure about that, yeah. I had a figure about that. Well, I will definitely explain this. Okay, this one. That one. Let me open this. Sorry. Yes, this explains well, I think. You can see. Okay, for example, you are in one phase, in your phase. This is your phase envelope that you described in your PVT. Okay, your phase envelope like this. When I was in reservoir, in my initial reservoir conditions in here, okay, when I was in reservoir, it's one phase directly. It indicates one phase. I'm outside of my phase diagram. This is bubble point pressure in certain place in your wellbore. Maybe you will pass this value, but it's not useful. For example, describe the depth of this. Okay, but when it reaches to your wellhead, you have to describe this one. When it reaches to your well depth, it will probably be somewhere like this for this example, right? Your wellhead P and T value. So you will be inside your phase diagram. You are now inside your phase diagram, right? So you have certain amount of liquid and gas production. When it comes to your separator, it will decrease more. Your pressure will decrease, your temperature will decrease, and you will be inside phase diagram for this fluid, but will be in lower point. And your tank conditions, it will be much lower. Okay, so you have to describe all of these to understand how many percent gas, how many percent liquid you have in that certain conditions. That's why we are using the phase diagram. You have to describe the characteristics of that, the composition and characteristics of that fluid. Okay, this is the reason of using the phase diagram. Okay,
Okay. I got.
So another question. Another question. not affected. How gas hydrates, if any, in dual energy gamma ray measurement? Gas hydrates also behaves the same behavior with foaming and emulsion issue. Okay, so the measurement the measurement is in micro scale. If I am making this micro scale, like this Floco Rotron Venturi in the beginning I said, single phase measurements or some part of the multi-phase measurements, then it will affect it. But in this version, the VX, it's when it is making by counting the gamma photons, okay? So gas hydrates also not affected the results. Why? Because that gas hydrates also formed by the different combination of this gas, water, and oil, of course, in it, gas and oil. So what happens if it reflects with another component apart from gas, water, and oil? It will not know. It will, because it is not described. Okay, it will not know that this, for example, this is what can I say? CO2. This is CO2. Okay. The calculator computer doesn't know the CO2. It just know water, oil, and gas. Okay, and of course sulfur. Sulfur is important. Oil, water, gas, and sulfur, because we are making sulfur correction. This is crucial. It just describes these phases. So if you are producing from gas hydrate, and if it comes to a gas hydrate molecules inside the gas hydrate. If it is oil and gas molecule, then it will count. If it is another thing, it will not count. Okay, so it will not affect it. The gas hydrates also will not affect it, the flow, the rate measurement. Okay. You're welcome. Any other question? Good questions are coming. Any other question?
Thank you, Mr. Hakan, for that useful and informative session. So, thank you. So, I think that we don't have any question. So, if you want to give some advice to the students about your experience about anything about petroleum, so you can give some advice to the students. It's okay. So thank you again.
You're welcome. It was a pleasure for me. Actually, in terms of advice, so you are already aware of that. We are dealing with hard days in oil and gas industry currently, right? So, but in short times, it will be changed, I believe. And when I'm talking with some of my friends, they are also agree with that. It will change. The wind, the direction of the wind will change soon. Okay. So the best thing that can be done, the first thing, is to enable, to maximize your communication with the people and experts in the industry, and to enable to be in contact with them continuously. Okay, this is the first thing that I can say, because how much they know you closely, they will interact you in a direct proportion with that, and then the chance to be involved in industry and awareness of yourself by the industrial expert will be easy. Okay, so being in contact is everything, and like a network. Actually, we are not a big industry. We are compared with the others. We are relatively small, right? So everybody knows each other. When you become within this industry in the future, inshallah, so you will be part of this industry. You will see that how small it is. Actually, it's small. So everybody is contact with another. So the communication is everything. Okay, is everything in this industry. So fulfill yourself with experience and in terms of technically, and if you can do practice, of course it's okay. And then be in communication with your big brothers, your friends, your instructors. Okay, so these are the crucial things that I can say. If you are a successful person, then you will find your way, and you will handle all the things in this industry, no problem. Now the situation is a little bit tough, but it will change soon, I am saying, and hopefully it will be better for all of you in the future. Okay, if you have any questions regarding on my experiences, previous experiences, background, whatever, I am glad to answer you. No problem. If you have, you can ask from here directly, or you can send me an email, or via LinkedIn, you can contact with me. I am using LinkedIn oftenly, very oftenly. So these that I can say to all of you, friends.
Thank you very much for that useful information. So I think we don't have any question yet. So have a good day. Good night.
A good day to all of you. See you in next week in the perforation techniques. This is also related to mostly related to the basic information that we gave in the first week. Okay, I put it to fourth week because I wanted to make a combination of all these 4 weeks. So perforation techniques, which is which is not known too much. Okay, technically in the industry. They have devices, guns, whatever. But what are these guns doing? What type of racks can be performed with what type of guns? Okay, in what type of situations? Under balance or over balance? The over balance perforation need to be performed. Okay, we will talk about these things. It's also crucial. So. See you in next week, I am saying, and thank to all of you for listening this crucial course. Thank you very much.
Thank you, Mr. Zhao. Thank you very much.
Thank you very much.
Thank you.
Thank you. Goodbye.